Thank you for your patience. We're going to get going on the next major topic here. So I'm going to be giving a brief talk about a very big, exciting area that's very central to our lines of contribution and has been for a number of years now. And that has to do with the confluence of, on the one side, system science, dynamic modeling, as well as other techniques such as convergent cross-mapping, with data science, a very fast-growing area of science which is focused on gaining insight from data, often very large volumes of data that is simultaneously characterized by volume, often high velocity, high variety, and high veracity. Within this talk, I'm going to give a very brief sort of glimpse of this emerging confluence of areas that draws heavily on our own work, but at the same time respects the fact there's just so much I'm not going to be able to touch on. But it will give a glimpse of some lines of great opportunity there. This talk will be followed by a talk by my doctoral student, Yan, back there at the back of the room, who is going to be talking about a particular application example which combines dynamic modeling and machine learning techniques as applied to measles and pertussis. So the motivation, as you recognize, for so much of the modeling that we've been doing, and indeed for the work here, is the fact that we're confronting very complex. I thought I did put lecture slides out for this. One thing I could do, and I'd be happy to do so, would be to see if I can put it out right now. So there's models and data benefit center. I don't think the exact latest versions of these are there, and so I will place them up there. It will take just a moment because I think there may be several related talks that I put there, and this would give you the precise slides that that I am covering. So give me just a few minutes. Of course, as we've seen, there's likely to be a little bit of a delay, getting this to you because of the way Google Drive works, unfortunately. And there we go. Okay, it is being uploaded right now. It should be there. But for some of you, because of the transit time, it will take a few minutes. Okay, so the motivation again here lies in the fact that we're confronting ever more complex health policy challenges which involve entanglement of a lot of different factors interacting over time along particular causal pathways. And I've argued in this forum that we're confronted by great challenges if we purely rely on reductionist techniques and techniques drawn from system science. This sort of science as a whole can help us visualize, understand, reason about the underlying processes that give rise to us, and can help us understand efficacious intervention options and share our assumptions with others, refine our thinking, and help us learn more quickly about these systems. And a central way in which we do this is through the use of dynamic models, such as we've been covering within this course. And I've argued here many times that these models represent hypothesized causal relationships, these generative pathways by which diverse factors interact over time, and often we have this coupling across the system that leads to entanglement of many different areas of the system that lead to changes in one area rippling through to changes in other areas. These challenges, as well as many others, makes reasoning informally about the impacts of interventions difficult, but with dynamic models, we can more reliably start to think through the implications of interventions in isolation or portfolios of interventions. They can also help us identify broad system vulnerabilities, ways we might be able to improve the system structure and coordinate the effects of actors. And here and elsewhere, I've argued these models have many uses. One of them, and a primary one of interest in this talk, is serving as what-if tools to identify appropriate policy portfolios, not perhaps just one policy, but several, or several interventions. To evaluate benefits of restructuring a system, to prioritize research collection, and fundamentally, and perhaps most deeply, to learn faster and more deeply from evidence. Now, a major barrier to this that struck me 15 years ago or so, and that motivated my first work in this area at MIT, lay in the fact that with these models, whilst we cannot articulate theories with the models, causal pathways that are quite detailed, we can have these agent-based models that depict interaction of individuals or processes within an individual at a very fine-grained level. Often we are pressed within the health sciences to marshal evidence that is at the level of detail that can fully inform this model. This became very apparent to me in the opening years of my work in tobacco policy, where I could find a great deal of evidence, often, for example, on intervention outcomes relating to prevalence of smoking, but very, very little on the actual behavior change effected by those interventions. I know they lowered the prevalence of smoking. How much of that was due to reduced uptake, reduced initiation? How much of it due to enhanced cessation, and how much due to lowered relapse was not at all evident from these studies. I found myself sometimes frustrated for lack of evidence concerning the frequency of relapse given different lengths of time someone had quit. Recognizing that the longer someone's quit, the less the nicotine craving often is operative on a daily basis, and the lower the chance on a per day basis, perhaps, that they'd fall back into smoking. But data at the level needed to inform some of my model assumptions was often lacking in the literature. It was lacking in primary data, to which I enjoyed recourse. And over time, within the health sciences, as my areas of contribution broadened, I found the same thing across many spheres of very, very relevant health behaviors, health exposures, and other factors. It has to do with, it comes up, for example, in understanding people's location patterns. You think someone should be able to, on the top of their head, report pretty accurately where they spent time. But if you only ask them once a month, the answer is going to be correspondingly coarse. Even if you ask them at the end of the day, our own work here at the University of Saskatchewan, with data measured from smartphones about where people actually spend their time, has shown dramatic differences from where they report spending time. So in some studies performed with undergraduates at our institution, studies which Narges and with Xiaoyan and Luce have contributed to in their broader form, some of those studies have revealed dramatic differences between the self-report of undergraduates where they spend their time and where they actually do. I'll give you a hint here. Undergraduates have an unusual predilection for reporting that they spend their time in the library, in other words, they're good students, spend their time at the physical activity complex, they work out, they invest in their health, and they spend their time, of course, of necessity, eating with friends and catching buses. If you actually look where they spend their time, it's often like night and day compared to this. There is some time spent in classroom. They don't tend to spend too much time in the physical activity complex, and they spend low amounts of time in the library studying. There is time spent in other places, perhaps Louis included. at hours of unlikely to merit studying. So location is often, whether through confabulation or through recall bias, or just the difficulty, the burden of summarizing where one spends one time through self-report, it's a challenging thing to elicit with traditional data sources, diarizing or recall how much time you spent X, Y, and Z. Physical activity is known since the NHANES 3 study in the States to be very subject to a lot of bias in self-report. In that study, there was a subset of individuals asked to wear accelerometers, actigraphs, I believe, and there were big differences between what they self-reported for physical activity and the actual levels of physical activity measured via the accelerometers. Similarly for dietary intake, asking people what they eat versus, in fact, examining at a physical level what they eat through plate weight studies or others, you can find some quite large differences. Even something as simple as weight, there's been some beautiful work out of StatsCan comparing self-reported weight on the one hand with actually physically measured weight on the other. And there are large differences. The differences are gendered, with men tending to overestimate their weight and women tending to somewhat underestimate their weight, but they are pronounced gaps. So many things similarly with spatial proximity. We ask questions. In our very first study here on the university campus, a study that Narges might remember back to, Winchell certainly will, we used these small sensor devices. We asked people to carry around. It was during the flu pandemic of 2009, 2010. And we asked people to diarize who they spent time with. So they're asked once a day, give us the people you spent the most time with. So it wasn't an ongoing diaries, once a day. And we compared that with what was picked up with the devices. And once again, we found really big differences between statistics. One of the big issues was that pretty quickly people just refused to write down who they spent time with. They found it so burdensome to do so, they just neglected to do it. Whereas we had a very high resolution picture of where they were spending time using these so-called modes. Same thing for communicational behavior, and even things such as decision-making rules and heuristics, so important for helping to nudge people towards healthier foods or to physical activity, lower sedentary behavior, are often, they're not well captured with traditional instruments. Similarly, exposure to environments, to different behaviors, whether it's the food environment, built environment, to behaviors of others individuals, say, engaged in physical activity. And the challenge is that absent an understanding of these behaviors exposures, for certain types of very quantitative analysis, the ability to accurately evaluate policy trade-offs that are dependent to some degree on these reliable understanding of these behaviors is really limited. So the thesis of this presentation, indeed the thesis of much of our work in the computational epidemiology and public health informatics lab, is that the advent of big data in health synergizes will fundamentally enable dynamic modeling for health policy. And I'd like to provide some suggestive evidence in coming slides as to why this is. So first of all, what do I mean by big data? Big data is a term that's dramatically overused. It's overhyped. It is used hopefully by people who have data sources sometimes that they hope will qualify for that catchy term. But there's a lot of understandable uncertainty about what this really denotes. And I'm going to put down here, without it claiming it's any sort of principal definition, on a bunch of features that I personally consider eligible for that criteria within the health context. It includes some somewhat more traditional large-scale administrative data sources. I would consider them big data for reasons we'll get into in just a minute. Point-of-sale records, purchases, for example, of personal protective products for mosquitoes. We've done some work looking at purchases of mosquito repellent, for example, over time. Data from environmental sensors. And I would also note communicational behavior, keyword search volumes online. Some of you may have seen the posters about that. Uses of Twitter and Facebook, for example, post status updates on Facebook or Twitter feeds. Something that Xiaoyan has done a lot of work with and that Lujie has helped with also. Beyond these things, there's, for example, browsing behavior online, which we can sometimes understand through logs for a given website, say a website providing guidance on how to secure vaccination within the Saskatoon Health Region. Look at logs recorded for infrastructural reasons that can help us understand the volumes of people coming to that site. Data collected by cell towers and by consumer electronic device sensors, this being a big area of data collection for us. What is it that characterizes big data? Well, the least objectionable definition that I found relies on what are called the 4 V's. It's characterized by volume. That's the V in big data. It's high velocity, meaning data comes in very quickly. For many of these data sources, multiple times a day. For some data sources, every 5 minutes, 10 minutes, there might be hundreds of records recorded, such as an accelerometer. So velocity, compared to traditional epidemiological data sources, velocity can be very high. The data arrives quickly. And that turns out, for dynamic modeling perspective, to be probably more important than just volume. Volume is one thing. Velocity starts to align it with the types of dynamic pictures we get in the context of our dynamic modeling. Jason, would you mind adjusting this to point back to another defined feature of this data is variety. Typically for a given period, for a given participant, a person, we'll have many sources of data. We'll know something about their Twitter post, we'll know something about their movement behavior, we'll know something about their contact patterns, we'll know something about their level of physical activity, and perhaps sedentary behavior, or perhaps answers to questions that we post them. So, same period of time, same person, you get this multidimensional portrait of this consenting individual. Finally, veracity side. This is not an attribute which can always be applied to a particular measurement in isolation, but often collectively, with several lines of evidence, we can get a better picture that's more reliable than what we get out of people self-reporting for certain things. I gave examples earlier, where people spend time. Something we get from GPS or Wi-Fi localization, we can figure out someone's location much more reliably. Physical activity, between accelerometers and heart rate variability, particularly with wearables, we can do a better job than through self-report. Dietary intake, if you're getting photographs of meals or photographs of receipts of meals or point of sale data more directly, you're probably far and away much better understanding dietary intake than through self-report alone, if only because it's far less burdensome and therefore adherence will be higher. In terms of contact patterns, what we can pick up for individuals within our study in terms of contacts with each other is much richer than what they regard via self-report. In other things, we turn to multiple sensors at the same time to help us elicit information. For example, is someone indoors or outdoors? Is someone in a vehicle or not? We can turn to many types of sensors. Accelerometers, yes. Velocity is measured by GPS, say, for a vehicle. We can cross-link it with bus maps to see if it's starting up and stopping at bus stops. We can figure out information associated with the environment, sometimes even from magnetometers. So veracity, in terms of the reliability of the data to elicit this sort of information that we're trying to get in a reliable fashion, often we can do better from elements of big data. Now, within the big data context, in health, we have a wide variety of different levels of granularity of evidence, of more coarse-grained and more fine-grained evidence. On the one hand, maybe you could put it kind of in this region. Thanks. Sorry for the trouble, please. So on the one hand, we'll have finer insights coming from mobile data collection, something I'll be talking about a fair bit in my vignettes. Data from wearables, data from smartphones. On the flip side, if we look at data sources that are high velocity, that qualify in terms of volume, velocity, veracity, and variety, things like search monitoring are far coarser grained. They're fully big data, but they're coarse grained. They only give us things, say, once a day for a given region. Twitter monitoring of these tweets coming out, can capture things at an individual level over time, so individually, longitudinally, but it's less voluminous by far than what we get through mobile data collection. Let's just take a look at a few of these. So if we consider search volumes, I argue that volumes of search data, searches for a particular term, can provide an indication of interest in that term or a term category within a region. And this is probably a little bit old now, maybe it's a year or two old, this statistic, but at the time I created this slide a year or two ago, it's about 60,000 searches per second worldwide. Okay? And within a given region, you'll very commonly find large volumes of searches within the course of a day. They are aggregate quantities. They don't tell us which person searched for it. Was it one person searching 1,000 times in the same day? Or was it 1,000 different people each searching once in the same day? But it does give us some sense of sort of level of interest. So this is from Anahita's work for Quebec, showing search volumes as judged by different terms. The interesting thing is each of these curves is a different term people could search for. Some in French, this is Quebec after all, some in English. And what you see is a pretty similar picture over this period of the flu pandemic. I think it was the deuxième vague, the second wave, where we see initially low, goes up, mediates over time, and has a longer tail associated with it. Many different particular search queries, but giving a somewhat consistent picture. This is for Australian searches for whooping cough, pertussis. It's actually the whooping cough is the term, though, but it refers to, of course, the underlying illness of pertussis. And what's interesting about this depiction for me is, of course, this apparent change of mode occurring about here. Prior to this, we get a rather qualitatively different set of patterns than after. After has higher search volumes by a factor of roughly 2. But more than that, it has these pronounced seasonal peaks associated with it. It further has much bigger swings. And something happened around here. And if you go in and you look into to what was going on at the time related to pertussis, you find societal fascination associated with this time period that reflects a very tragic case. It's the case of baby Riley. It was a child in his first few months of life who lost his life to pertussis. And he was not vaccinated per schedule. And tragically, he died from this disease. It catalyzed a great deal of awareness about the risks here, the vulnerability of children, and led to much greater levels of interest in subsequent years. The interesting thing is if you look at this for a period of many years, this is only, after all, somewhat over a year here. If you look at it many years, it returns back eventually to the pre-awareness indication. This Canadian searches for naloxone, the opioid antagonist, used amongst other things to intervene in drug overdoses. And you see here writ large issues of concern for opioid-related emergencies as they play out over a period of many, many years. Interestingly, with these sort of search volumes, you can restrict your interest not only to certain ranges of time, but also to certain geographic ranges. The ranges are coarse in many areas, particularly here in Canada, in Saskatchewan, where population densities are less. We can get searches within our province. In other regions, you can get it within different parts of areas. For example, Massachusetts, you can get Eastern versus Boston, metropolitan Boston versus, I think, maybe metropolitan Worcester, etc. The point is, you can get some sense of the geographic origins of a lot of this sort of data. So, ladies and gentlemen, that was search volumes. I'd like to now talk about social media data, and I'd like to distinguish two types of data. Those in the room are likely universally familiar with social media platforms. It's hard to function in today's society without being. Social media platforms are, however, globally perhaps more diverse than people in North America will obviously realize. In North America, I've listed some prominent social media components, but even these have variants. For young people, of course, Facebook is on the wane. Snapchat and Instagram are particularly popular. And I would put YouTube up here, because it's a social media platform. Among certain subcommunities, like the Chinese subcommunity, WeChat, and in fact, East Asia community, WeChat is wildly popular. I'm pleased to be connected on that network. But in other communities, such as the South Asian community, I understand Viber is particularly active. And in general, there's a whole shifting, miasma of different explorations on these platforms, each quite different than the other. One thing that is notable is that on different platforms, there are great differences, not only the type of content, Instagram for higher quality pictures, Snapchat for informal, self-destructing bits of pictures, but also differences in privacy expectations, for example. Some of these, and these are the ones which we turn to the most, are self-publishing platforms. This is extremely important for ethics reasons. From an ethics perspective, long before we started this work here at U of S, we went to our behavioral and biomedical ethics boards, research ethics boards, or institutional research boards, and we sat down with them and said, look, this is what we can do technologically. What are the proper spheres in which this could be done with foremost ethical standards? And we have adhered to those, and I'm very pleased to say that we've really addressed the ethical side of our commitment strongly. And one of the ways in which we do that is by focusing on self-publishing platforms like Twitter. Twitter is a platform designed for self-publishing. It's designed to share information with others. People can sign up very readily, and you can search online for people's Twitter feeds, even not being a subscriber through standard Twitter interfaces made possible, online website for Twitter, TweetDeck, etc. And it's in the open. It's contributed to public discourse. By contrast, something like Facebook has a reasonable expectation of privacy that prevents you from ethically delving into it without consent of those individuals. And of course, those groups, such as Cambridge Analytica, and the Russian purchasers have done so at great ethical peril, but they're well protected within certain spheres, of course. So the privacy expectations are very different, and one can't just clump these all into the same source. They do provide a glimpse of diversity and attitudes and beliefs across swaths of the publication, across the population, and there's a strong, as we said, variation in use. So I've noted Twitter as a public platform for expression, and it has somewhere over 300 million users. In the US, it's about 60 to 70 million really active users, many workers there, and it has quite a high volume. I think it's now fairly regularly above 10,000 tweets per second worldwide, but it's possible it's still sort of touching that limit. For many tweets, not all, as Xiaoyan knows, but for an important subset of tweets, you can either directly have indicated in the tweet its location source, so that it's from a certain city or a certain town, for example, or it can be actually geotagged, in which case you know it's from this certain, GPS location. And there's been some really fascinating work done on geo-inferencing tweets. So figuring out, almost certainly this tweet is from here based on certain type aspects of the social network or the history of the tweet, the words used, etc. And you can filter it by content, by time, by geography within these limits, and crudely with sentiment. The interesting thing with tweeting is that retweeting provides an indication of interest or agreement. People can like tweets, which gives an indication of attitudes towards these things. And through fairly straightforward textual analysis, you can extract a fair bit of understanding. Through more detailed natural language processing, you can understand much more nuanced things, including sentiment more reliably, etc. Tweets provide you a fascinating picture of attitudes, beliefs, and in some cases knowledge about particular subjects. So if a campaign is put out there for vaccination, for example, you look at the tweets which reference that campaign, and you can look at how they change over time, the dynamics of it, probably rising very quickly as the campaign starts and then decreasing over time, and perhaps with further advisories rising. And you can look at the content, the messages. What are they saying? Some tweets that may be anti-vax tweets may take up certain lines of argument or have certain counter messages that they engage in. And by understanding those counter messages, public health agencies can get ahead of them and potentially respond to them. So not looking at these sorts of data sources blinds one to a wealth of information about people's knowledge, attitudes, beliefs with respect to health phenomena, but also with respect to interest levels. And that's what I'm going to be coming to as well. So we have, for Canada, large tweet databases that we've been amassing. Li Xiaoyan back there has done so for Alberta, and some others in our group, myself included, have done so for Saskatchewan and Manitoba. So for Saskatchewan, we get on the order of 1 million a month, something like that, of tweets, which are imperfect. They're very imperfect for Saskatchewan. There are some that come from neighboring regions because the way we're doing it, and we have a more precise way of doing it and a less precise way of doing it. That one is more includes ones that are uncertain, and one excludes those, with each over and underrepresenting those. But Twitter is an incredibly valuable source of understanding of attitudes and interests over time. And the dynamics there, if anyone's interested in seeing them, I could show examples. They are completely fascinating. To look at how communities respond to new issues, the emergence of Juul, for example, these electronic cigarettes in schools, it is remarkable to see the dynamics associated with that. Tragedies such as the Humboldt Broncos crash in the province. It's just seeing the dynamics associated with community response for that, community healing, the changes in level of volume over time with respect to that, and tragedies like the Colton Bushy shooting, which has strong societal points of concern associated with it. You can also see dynamics associated with them. So we do a lot with tweets, and I'll probably refer back to them later. But the final one I want to talk about is consumer electronic device sensors, because so much of our work has been spent in this area. And starting in 2010, we built our first generation system around smartphones for epidemiological data collection. And the goal here was to build a system that would have the requisite flexibility to be retargeted for a wide variety of different epidemiological needs without programming, or with a very minimal programming. So the idea is we should be able to use the same system and simply re-specify. Say, I want to specify a study like this. Maybe it has these questionnaires triggered by these conditions, this type of sensor data, this sort of contextual data picking up, used with these wearables, and we have that study specified without getting a programmer in the loop. That was the vision. And I'm proud to say, standing here, that we've realized that vision. We have a very flexible system. The third generation is Ethica. This spun off about 5 years ago to be a company once the service requests were at such a level we couldn't reasonably support it in our labs. And it's targeted at Android and iPhones. It runs on typically participant smartphones. Occasionally for lower SES groups, we hand out smartphones. So for example, for homeless individuals in Regina, we're tracking a cohort of homeless individuals. Tina, my graduate student, has been central to that. And many of these individuals are homeless. Some are poor individuals who own their own, do not have their own phones, but gratefully accepted them from the study. Others are higher SES individuals who have their own phones and just installed it. Typically, for most studies, we install it overwhelmingly on people's own phones because they want to carry them for other reasons. But for particularly vulnerable people, we do sometimes hand out smartphones.
This came up only because I know it happened in CNH and grants with you.
Sure.
Do you have it acceptable on both platforms, Android and
Yeah.
Yeah.
Yes. It runs completely seamlessly, same study specification on both platforms. Yeah. And I will tell you this. There are the occasional features. So I'll give you an example. Detection of Wi-Fi networks. Okay? Detection of when you're in contact. Let's say within our province, Saskatchewan Health Authority, the new amalgamated health authority, maintains Wi-Fi networks of certain types in all the major hospitals. Okay? And through detection of Wi-Fi, we have an alternative to GPS for knowing when they are in contact with a healthcare facility, because we can look at Wi-Fi contacts, which is a little bit more specific because when they're inside, you might not have GPS signal, but you'll see the Wi-Fi. Wi-Fi is only available. Wi-Fi detection is not allowed on iPhone. And so that is something that is platform specific, okay? Screen state is on, the vast majority on both platforms, but there are a small number that are only available on Android. That number is shrinking because Android is becoming more tight as a platform. It's becoming, I'll give you an example. With Android phones, for many years, we used to rely on Android for phone-to-phone contact. So phones could detect each other. This would be for consenting phones only. For example, in the study, one phone would directly detect another. Okay? And we have many, many studies where we have beautiful social network dynamic information. And we've done many studies of simulated disease propagation across these different networks based on proximity. Because it detects when people are proximate, roughly how far apart they are. Now recently Android has followed iPhone by restricting that further. And what this means is now, to do this, you can still do it for both platforms, but what you need is what's called a Bluetooth beacon, and you can stick it on the back of the phone. It's something that kind of looks like, well, they vary in form factors, but they can look like this and so on. And basically, that is an explicit indication that, like, I'm here and to be detected. And both platforms are getting a little bit more, well, particularly Android is getting more picky about restricting some things that are traditionally open. But the vast majority of things, vast, are available for both platforms. and they're available completely interchangeably. So it's certainly the same study definition. Okay, so this uses what's called bursty data collection. It collects data about every 5 minutes in a really quick way. Spends maybe a minute measuring physical activity through accelerometers, for example, measuring things like distance to these Bluetooth beacons, etc., and things like GPS location, etc. And this helps prolong battery life. It really has very little battery footprint in the most cases now, with the exception of there are certain sensors that will have a modest battery impact in the latest version. It has diverse sensor modalities, and you can have some context-triggered surveys. And it has a variety of modules. There are some plugins that you can install separately for things like smartwatches, and for monitoring things like browsing behavior from consenting individuals. So the areas that we're addressing, not surprisingly, map directly onto those that I listed earlier as being challenging. Things like location, physical activity, spatial proximity, social context, and communication. So it allows us to kind of map activity levels over geography, as well as many other features. We can join together this data. A goal of this from the very start, before we started, again, we went to our boards, and we built in snooze options, so at any point in any study, people can snooze the data collection, can say, look, stop collecting data on me for an hour, I want to opt out. They can also leave a study, and they can leave questions unanswered. It has strong on-device encryption. There's actually 2 levels of encryption, and it sends things back in an encrypted fashion. There are certain types of information we do not collect because of privacy concerns. And there's an informed consent process that all studies go through, sometimes in a tiered way. So this is a little bit about our study, our system. We're going to see more about it in the particular vignettes that are coming up. So what is this linkage between big data and dynamic modeling? Well, fundamentally, I'll boil it down to just a few things, recognizing the full story is more catchy. First of all, big data can provide empirical evidence to inform policy modeling. We can use the evidence as gathered from these phones to inform our understanding of model parameters, to better calibrate a model, and in order to reground a model over time. We can also use both tools jointly to learn quicker from intervention effects. We can, using machine learning tools, I referred to it earlier, we can reground the model in data and kind of keep it current and keep it in line with the latest evidence, and can use it to inspire interventions. I'll say further that dynamic modeling can prove big data by telling us how frequently we need to collect data and of what types. And I'll see if I can touch on that before I finish here. So we have a wide variety of studies, some of them conducted, or very fortunate to have conducted some exciting work with Cheryl there. And I'll talk about a few elements. Sometimes people talk about machine learning and AI's relationship to theory. The study I'll be talking about now helps explicate theory. It helps better understand the consequences of theory. And this is focused on outbreak response. Some of you saw the poster associated with that. So I'll go through this very quickly. But fundamentally, health authorities have real challenges in responding effectively to outbreaks, particularly outbreaks of new and emerging infectious diseases, things like H1N1, or newer infections like SARS or MERS, etc., which have big unknowns associated with it. We can get insights from frequent, say daily or weekly reporting, but it doesn't tell us what lies forward. It gives us a sense of where we come from, but not much for going forward. And our interest in this area, and the interest of some of our collaborators, such as Alberta Health Services,
has lain and trying to anticipate the trajectory of cases going forward. So the question here is, can we create an automatically updated system for theory-based prediction using empirical data? And particularly, how can big data inform this? So we examined for this actually a system dynamics model. We've done this sort of work with agent-based models. This was a system dynamics model published in the literature. It's work actually Megan referred to as work by Epstein and Hammond, as well as others, which characterized, as they put it, the dual contagions, the competing contagions associated with, on the one hand, pathogen, infection, proceeding from susceptible to infection to a recovered state, but also spread of anxiety associated with this, particularly when you're dealing with things like H1N1 influenza. And they have a model behind it I won't go into. A detailed model, but we reconstructed this model. We clarified some aspects of it that were not clear in the original paper, that were left understated. Now, we had data from 2 big regions that we wanted to test this system for effective prediction using this data, using machine learning methods jointly with dynamic modeling. One of the sets of data was from Manitoba, where we had data from clinical diagnoses, ICU admissions, et cetera, and from Quebec, where we had data on 2 ways of infection. So we sought to leverage this model together with machine learning tools and aspects of big data. So we made use here of the coarsest form of big data that I mentioned earlier, search monitoring. And particularly, we looked at Google searches for each of those regions, for the Quebec region and for the Winnipeg region. Here, we were looking at a historic period that's just one of just a subset of the broader period in which seasonal influenza searches are a familiar feature. It was one where some of the search volumes were highest, but where ultimately it was a subset of this broader picture. And we drew in this work a technique that Xiaoyan will be leveraging in a case study after this, which is this technique of what's called particle filtering. It's a sequential Monte Carlo method. It's a Bayesian technique that has close cousins in Markov chain Monte Carlo techniques and particle Markov chain Monte Carlo techniques, which hybridize the two. These are techniques for particle filtering for estimating the latent state of a dynamic model based on incoming data over time, and in some cases estimating the value of evolving parameters. So what is this particle filter? Well, Xiaoyan will show you an example later, but fundamentally it's a technique that allows you to run a simulation model, not with just one best guess for what's going on at any one time, one depiction of the current state of the model, but with a wide range of simultaneous hypotheses. Maybe we have more people in this state, maybe we have fewer. We have hypotheses of different possibilities within the same model. The simulation model here typically includes stochastic processes. It includes some uncertainty over time, like the models we've been dealing with. Agent-based models are great to be able to use in this regard because they have good representation of stochastic processes. It doesn't make sense to use this technique with a purely deterministic model, and the model that we were using did incorporate some stochastics. And basically, it runs the model over time with a wide variety of hypotheses, not one conviction of this is going on right now according to the model, but a wide variety of hypotheses. And what happens is, between observations point, those hypotheses are just advanced forward. But when new data comes in, there's a survival of the fittest. The hypotheses that are consistent with that new data where the model is predicting things consistent with the new data that are not at odds with it, those are propagated. Those are viewed as being fit in an evolutionary sense and continued on through a process known as resampling. Others that are not compatible with this observed data, where the observed data runs counter to what the model's expecting with that hypothesis, have a tendency to die out. They disappear. They're weeded out. This is survival and short of the fittest. But the fittest here, ladies and gentlemen, are not organisms, but hypotheses. But hypotheses as captured by what's called a particle. Each particle represents a possibility, a possible hypothesis. And particles have weights according to how plausible they look by comparison with the data. Now, this whole process is performed recursively. And what this means is, without getting to the technical jargon of it, what this means is when each new piece of data arrives, in principle, you don't have to reconsider rerunning the model for all the previous data. In principle, if possible, just run it forward using just this piece from the estimates from previous pieces to the next point. So when new data comes in, it doesn't require rerunning the whole thing to that point, but rather incorporating that and moving forward. So here, we're sampling from this distribution of trajectories of the model. So over time, what's going to come out of the particle filtering is not just a single model trajectory, say, in terms of the number of infectives over time, a single privileged trajectory of what it thinks best matches the data, but rather a set of possibilities, almost a distribution at any one time. But it's a distribution of trajectories. So some trajectories are more viewed as more likely than others over time. And there's the survival of the fittest that makes this possible. This is particle filtering. I'm trying to explain it at an intuitive level. Li Xiaoyan will show you some examples with it. So we took this model, and we had likelihood functions, which basically line up. On the one hand, they ask, given this hypothesis, the fact that the hypothesis in the model says there should be, say, this many people infected now, this many people recovered, this many people in fear, for example, to what degree does that match? Oh gosh, some of the math here is yellowed out. But to what degree does that match the empirical data? So the likelihood function, if it's a really good match, likelihood will be high. The likelihood of observing this data, if it's a poor match, the likelihood will be low. And that's what's used to kind of weed out some of these hypotheses, these particles over time, or associated with lower weights, which leads them to draw. So the empirical data we have was from Quebec and from Manitoba. And as you probably saw in the poster yesterday, when we brought in new data, we could use it to constrain the model. So the idea here is that we have data here up to a certain point, and using only empirical clinical data, using only the finest data type that we're going to be using, the clinical data to this point, we tried to project forward using this model. And these different hypotheses. And what we found is if we only use data from here and we tried to project forward, we became very quickly very uncertain about what would happen. Sometimes the model said it was going to be a very high incidence, sometimes a low. Same thing with predicting search volumes going forward. We tried to predict clinical cases going forward and search volumes based on this model and the empirical data and particle filtering. But interestingly, if we brought in the data from search data to accompany this clinical data, this was actually the search data. We had clinical data separately. If we brought both together, it made the model much more confident about what was likely to happen. Now, this is somewhat counterintuitive because normally we think of clinically diagnosed data as the real gold standard, or at least it's much more high quality data. It's much higher up in terms of the data quality than search volumes off of Google. I mean, that's very noisy. It's very ambiguous as to what it means. But it turns out if you bring it in, it's an independent data source. It has lots of independent information there. And it's information about a different thing. It's not information necessarily about cases as about anxiety about cases, which is exactly what the model was characterizing. And if you include that in your characterization, in your machine learning algorithm, you can become actually quite good at estimating how many cases there are going to be over coming weeks and months, how many cases are going to be, what the search volume will be. Now, this is actually not the very latest results. The latest results were shown in Anahita's results, so I realized I need to update these. But similarly for Manitoba, if we only use clinical case data, only one likelihood function, all we have is data till 35, that's right about here, we quickly become uncertain as to how many clinical cases there'll be. By contrast, if we bring in both types of data, it gives us a quite better picture. There's still some uncertainty, but it's the high probability density region, the highly likely region, covers this area, which quite closely matches the number of clinical cases. Same thing for search volumes. And if you look at the level of discrepancy of the model predictions from data, it turns out that with clinical likelihood and with Google likelihood, you're quite far off for each of them, and sometimes strikingly so for clinical. These are a bit different with the latest results, but for the two likelihood functions together, you can achieve much better. The whole is much greater than the sum of the parts. You can really, really reduce the uncertainties. Now, I like to argue that this technique more deeply gives us something better than just prediction. It gives us a sense of almost an imaging of the population. I like to refer to it as population tomography. It gives you something that's quite akin in some ways to what you get out of a CAT scan or an MRI. Let me, while it sounds implausible, let me walk you through the analogy. With an MRI or a CT scan, it's widely known that these can give quite exquisite three-dimensional portraits of the body. What's less well known is the way in which it achieves that. What happens is, and it's reflected in its toroidal fashion here, that it images you from many different directions, many different angles. And what happens is that it gets a whole lot of images, a lot of slices from those different angles. Now, each of those slices is terribly incomplete. It's terribly limited. It's terribly limited by, say, occlusion. If it passes on a given angle through your femur, it might block things downstream of that from appearing in the image. Or maybe it only has a field of view that includes a certain part of you. But you start putting these together, and collectively, they actually start to tell you a lot about what's going on in the body. You put them together and you get a three-dimensional portrait of the body compartments, of these different areas of the body. Any one image is highly imperfect, but the whole is greater than the sum of the parts. You get this complete sort of picture because they all link in with each other, and you get them to give a consistent picture. And I would argue that a similar thing is happening with particle filtering, because what it gives you, and this is actually from Lee Xiaoyan's work. I don't know that she shows this in her presentation, so I'll just highlight what comes out of these methods. It's fascinating, well, at least according to me. What comes out of the methods is you feed in this data, in this case about just a few things in the model, the observation of search volumes and the number of clinical cases. And what you get out is actually a picture, much like comes out of the CT scan, of what's going on in many different areas of the system. And the reason is what I commented to Megan earlier this morning, which is that when you have a highly coupled system, where A interacts with B and C interact with D, which also interacts with A, if you actually have information from any one part of the system, remember the lynxes and hares, which Wade kindly condescended to show? Information about one thing. The hares tells you about a lot about the lynx population too, and vice versa. So knowing about just these couple things in the system, these different slices of the system that we see in the data, actually illuminates different areas of the system. So it gives you a picture of the latent state of the system of different, in this case, compartments of the system, different ones of these sort of stocks within the system, these different categories, which if there's time, I'll try to explain in a system dynamics context later in a separate lecture today. But the idea is that we actually get out of particle filtering, not just the ability to predict forward. I mean, that's part of it, and it's a pretty nice thing. But that reflects simply an extension of the fact that what it gives us is an estimate of the latent state of the underlying system. It gives us a picture of what's going on in the underlying system right now that combines the model estimate of what should be going on now, based on running it, with what the data is telling us is going on right now. So what this provides is, over time, as each new data point comes in, that's what these red things are, as each new data point comes in, it's regrounding the model using that new data point, and it's updating its understanding about what's going on. It weights, yes, what the model's predicting, but what the model's predicting is a whole set of possibilities. It's a whole set of hypotheses. And each new data point clues it in, oh, these hypotheses are most likely. Weights them upwards, and therefore the model's getting more and more savvy. It's learning, ladies and gentlemen, from this incoming data. It's learning from these observations, and it's growing more and more clear about, okay, all these things we haven't observed directly. In this case, it's from Xiaoyan's work. I think this is for measles. It's estimating, for example, the exposed population, which is not yet infected, so they're not going to be presenting for care. The susceptible population, which typically we don't know about. We don't have good enough screening data or anything to estimate them. What we do know about is something about the infected population that are presenting for care. And then the recovered population, we don't observe directly either. But the data, the logic of the model, the fact that, look, if we're getting lots of infections now, there's got to be a lot of susceptibles, for example. Between the model and the empirical data, it tells us about what's going on in other areas of the system. The model logic, in order for us to see what we're seeing now empirically, it tells us what's going on in other areas of the model. And that's what's happening here. The model captures these linkages between different areas of the model, different features in the model, and the empirical data keeps it grounded on an ongoing basis. What you see here is the red line Xiaoyan put at a place to reflect we have data to this point, and then after there we'll predict. And what you'll see is the impressive ways in which she can predict for measles and for pertussis using this data and anticipate a coming outbreak, for example. So, in short, the ability to predict forward is just an extension of the ability to estimate the current situation in the model, which in some cases includes parameter values that are changing over time. For example, changing contact rates or changing reporting rates associated with new cases. So Xiaoyan will explicate that for the case of measles and pertussis. This is something Xiaoyan will cover, so I won't cover that. It's due to her other work. Now, one of the nice features, which I'm not sure is going to be featured in your presentation, Xiaoyan, I think it may well be, I'll let you handle it, is intervention, asking about interventions. So not only if you estimate the current state, can you ask, well, what will happen if we do nothing? But you could ask, what will happen if we undertake an intervention? Do you talk about that at all in your presentation? Good. Okay, I'll leave that for you then. Okay. Okay, this is your stuff. Okay, so we've applied this very happily for a variety of areas. The opioid epidemic you presented on last night, and TB, chickenpox. Liu Jie over there led the chickenpox chickenpox work, measles and pertussis with Xiaoyan, West Nile virus by another student, Tong Peibo, and ED waiting times, Wade. Wade contributed. Okay, here's another vignette. Service dogs, ladies and gentlemen, service dogs. Veterans with PTSD, post-traumatic stress disorder, suffering from flashbacks, suffering from poor sleep quality, suffering from sudden anxiety attacks. We were interested in trying to use technologies in the form of Ethica to understand the ways in which service dogs, the presence of highly trained service dogs trained through this very rigorous training program led by a group called Adiamas, which is run by those, including many individuals with lived experience of PTSD. The ways in which the service dogs affect the trajectories of these individuals. This is a small end case crossover, though it's currently in the process of anticipated larger expansion with extra funding from Health Canada. And we are interested in the dog's impact on outcomes for the veteran, including substance use, flashbacks, suicidal ideation, and social contact. So we're interested in understanding the impact of these highly trained service dogs on well-being of veterans with PTSD and opioid use disorders. And the challenge here is the fact that individuals who are paired with a service dog have many impacts on their lives from the service dog. The service dog, at its most basic level, provides some companionship. You have a dog at home, and the dog provides a measure of a fellow companion in life. But there's many other impacts as well that lead the impact to be quite pervasive collectively. For example, the time spent engaging with a service dog requires the veteran to undertake certain structured activity in their life. They need to take the dog out regularly, they need to feed it, etc. And that leads them to have a certain structure. They can't be out for days on end, all around town or all around the province. They have to be back there to take care of the dog. And that leads to some structure in their life. And some might hypothesize that that leads to a sense of well-being. In other cases, there's direct impacts of some of those intermediate factors. The time they spend outside of the home with the dog, bring the dog outside to go for a walk, leads to less sedentary behavior. This is a major issue with some of the veterans. Dysphoric feelings, sometimes coupled with substance use issues, might cause them to spend large amounts of time sedentary in the home, which takes its toll on physical health as well as mental health. But the time outside home can also lead to opportunities for physical activity, playing frisbee with the dog, running with it, etc., which can also improve physical health even separate from sedentary activity, so moderate to vigorous physical activity. The time spent engaging with the dog outside also leads to some social contact with others. It's an intriguing feature I never realized about dogs, but service dogs as a particular example. Jason would appreciate this. As you take a dog out, you meet people. And the interesting thing that was pointed out to me is, if you have a dog on a leash and you go out and meet people, there's you have a degree of latitude in how close you get to the people you meet. They have their dog on a leash, you have your dog. How much you want to strike up a conversation and how much you want to stay quiet is a little bit up to you. And over time, you may choose to come a little bit more out of a shell, or you may choose, if you're not feeling up to it, to be a little bit more quiet and simply move on. There's always that chance to talk more closely. There's that chance to simply pass on that for now. And so it can lead to social contact with others in the community and sense of companionship from those, a sense of belonging, a sense of well-being in the community. The time outside the home can also lead to contact with the service, can be in the form of contact with the service dog community. These are individuals who come together for training with the highly trained service dog with other members of their community. So they meet others there, and it can lower the sense of isolation as well. Intriguingly, and this is something I never would have believed possible until I saw a demonstration of evidence that demonstrated it to me directly. The dogs are trained to recognize for their particular owner the symptoms of stress in that owner. They're trained to recognize the unique patterns of stress that owner undergoes, whether it's rocking and holding themselves, whether it's crying out or whimpering, whether it's lying down in just a way that covers their eyes, whether it's through anger or what have you. They train to recognize. More profoundly yet, or of equal importance at least, they learn to recognize the unique features of flashbacks in that owner. How flashbacks draw that owner out of sleep. Some owners cry out, apparently. Some sit bolt upright without crying. And dogs are trained to learn to undertake what are called interruptions. When I first heard the term, I thought it was considered a bad thing. They're interrupting needlessly the veterans' activities during the day. But it turns out, no, it's actually interruption of stress, interruption of distress. And what this can lead to is the flashbacks can get short-circuited before they get serious, before they get visceral. The dog can wake them up. Can, depending on the nature of dog, jump up on the bed, think of black lab, and lick their hand. Think about a chihuahua maybe nibbling at their ear or something like that, right? So intriguingly, we have opportunities for flashback. But the challenge here scientifically is, if we see outcomes for the veteran, an improved sense of well-being and lower risk of suicide ideation, why? Which of these pathways were the primary ones? Which were key drivers? Well, I'm going to show you how we use these devices to give insight into it. And here we're using mobile device collection. This is Ethica. Again, each study here can have a separate user interface with its own buttons, its own background, its own choice of which sensors are sampling, and its own questionnaires, including conditional, these days looping questions, variable substitution, etc. And they can evolve within the study with no programming required. So more sophisticated things where you can have triggered surveys, some of those require programming and some not. For example, in this case, no programming was required to bring surveys onto the veteran's phone when they were near the service dog, or when they spent more than 8 hours away from the service dog. It could ask, why haven't you spent time near that dog? We said, what have been the barriers to you spending time with the dog? What are your feelings towards the dog? To better understand where the barriers are. So the study included interviews on the smartphone, surveys, as well as sensor data. We have Fitbits on the veterans to measure heart rate and measure sleep quality. And we use interviews as well as classic survey instruments as well. But a large part of the data collection is with these microsurveys, which include photo elements for the veteran to submit photo and audio questions, answers as well. The Bluetooth beacons were placed, I'm told by Christine not to say mounted on the
Do not say mounting
on the dog. Christine would very much invade upon me to not.
The dogs have been mounted with beacons. Whoa! I said no. The dogs have beacons on their collar.
Yeah, the dogs had beacons placed on their collar. Thank you, Christine. Just in time. And what that allowed us to do is to track how much time the veteran spends with the dog, because we can detect the proximity of the veteran's phone with the dog's beacons and can measure that distance and whether the dog is within visible distance. And we could trigger surveys when they were not, or in principle when they were very close nearby as well. So these were some of the sensors that were collected. Nell, my student Nell, who you've seen.
When he sits back here with a small dog named Cozy. So as long as the dog doesn't know you, she won't go absolutely ape and want to see you. And Cozy sits on her lap when she's stressed. And Cozy will cuddle at her chest and she will touch her so that Nell has to touch her back.
Yeah. And so these phones were configured by specifying with Ethica what to collect, and with a set of surveys that Nell put in there.
You know, we should look at this one for prisons who work with prisoners who work with dogs.
I would love that.
Yeah.
Yeah. So just to sort of,
Is right.
thank you very much, to sort of catalog how these things relate. For Bluetooth big signal strength, we know how much time they spent with the dog. GPS accuracy and availability and charging time, how much time they spend inside and outside, we can approximate. Contact with other Bluetooth big beacon signals from other veterans, time spent with other veterans in the program with their dogs. GPS location, and by the way, we could have given Bluetooth beacons specifically to the other veterans to carry in the sort of way I showed you, to be detected themselves separately from their dogs. We didn't do that for a study of this sort with dogs specifically and beacons. We want to keep it simple. GPS location, we can know something about their entropy, the predictability of their routine. Are they going in a more predictable routine than early before the dog was trained? And we can look at their geographic mobility. We can also look at accelerometry and heart rate from the Fitbit for physical activity and sedentary behavior. Sleep length and regularity, we can get an understanding of their sleep quality following the dog and compare it with what was in place before they went through this training program. And accelerometry, heart rate, and time, we can understand something on a less fine-grained level about flashback occurrence. We can also ask questions, as we do, about their mental health and functioning and suicidal ideation. So we use this interviewing and traditional instruments as well as on-device surveys for things like PTSD symptoms, quality of life, substance use, reasons for separation from the dog as triggered by the beacon. So what this gives us is the biographies of which I spoke not 6 hours thence. The biographies, to quote the memorable McDonaldian term. So these kind of pictures over time of a veteran's story with their dogs. Occurrence of the dog arrival, acute flashbacks, instances of poor quality sleep, social engagement opportunities, dog interruptions of flashback, and moderate to vigorous physical activity and degree of sedentary behavior throughout this time period. And we can start to look at the patterns associated with this, much as we could look at patterns in a model. So while traditional instruments give us some sense of what's going on here, for example, how much self-report, how much companionship they've felt from the dog, or the level of physical health, sense of well-being. What we get with a smartphone-based data collection is something much more than this. We start to get pictures of how much time they're spending with the dog, the time they're spending outside, their actual physically measured and validated levels of physical activity as sedentary behavior, companionship for the dog, or the structure in their life as measured through entropy, their sleep quality, flashback occurrence. You get a much bigger picture and a much more fine-grained picture, a higher velocity picture. Now, the opportunity here is to distinguish, using these different pathways. Which of these pathways are most pronounced? When the dog came, did it really nudge their physical activity only minorly, but their sedentary behavior was reduced by a lot? Or do we see only modest change in each, and it's really structure in their life that was significantly changed in flashback occurrence? We can start to probe along which pathways did we see large effects, along which pathways did we see small effects compared to when they started in the study, which is prior to having a trained service dog. So here we can use measurements at many points within the system. This gives us longitudinal information. That's what the nature of this picture is, to have a sense of how big the changes are before and after. And in the context of randomization, we can help distinguish, which pathways are major drivers and the primary reasons for lack of intervention success. There's another study I conducted with Cheryl on foodborne illness. Yeah. It's the first paper on it is making its way now through the composition process. So it's not yet published. I'd be glad to refer you to our colleagues if you're interested in knowing more about it or seeing official documentation about it. I could also share with you some of the specifics on that too. We have a lot of the study protocol, for example, which I'd be glad to share.
If you
Yeah.
enjoy the dogs and stuff, the interact, could you call in as a Facebook page for
Okay.
it kind of tracks the. I love the dogs. They're really
Yeah.
Actually, the dogs themselves, but in chronic care, so it's different. It's
Yeah.
It's the same concept.
Yeah. Yeah, yeah. Now, we're using some data science techniques to look at actual pathway changes in pathways and to try to infer causal connections. There's this technique CCM, which Jeff alerted us to several years ago, which we've been evaluating, and which seems particularly promising for this level of quality and extent of data. The data I work with Cheryl, I'll go much quicker for here. I won't be presenting much detail on it, but fundamentally it had to do with foodborne illness, is guided by Cheryl's deep knowledge in this area. And we had a model which included a variety of components in it, involving reporting of cases, clinical presentation of individuals for clinical assessment, exposure to contaminated foods, food seeking, etc. And in the model, being an any logic model, it's one that Aiden could help show you if you are interested. We had individuals, for example, progressing. This is misleading, as Cheryl pointed out. The actual terminology here is just minor symptomology and major symptomology. The idea being certain symptoms bring people for clinical presentation and others do not. So it shouldn't be called subclinical, but so much as clinically presenting or not clinically presenting. Among food vendors, we have a distinction. Each restaurant or vendor could be in a state, at a contaminated state or an uncontaminated state, and an inspector went between them. There were some important uncertainties that presented when we first came out with this model. Sarah McPhee-Knowles' work in this area is published, and if anyone's interested, I'd be glad to share that. It's described in her thesis as well as other forums. And in the study, which Cheryl really brainstormed and led, we had individuals able to indicate when they were sick or when they were eating. So they could report when they're sick, for example, and be asked questions. Did they consult a healthcare professional? Cheryl pointed out, because of the high preponderance of students, probably asking about consumption of alcoholic beverages would be advised, because it might factor into symptoms. And they could report the nature of their symptoms to be able to distinguish a plausible, highly credible gastrointestinal illness that might be foodborne in its derivation from others that are unlikely to be foodborne. So one of the challenges here is that traditionally the amount of data available on cases on foodborne illness is terribly incomplete. Cheryl analogized it not just to the tip of the iceberg, but the spike of the tip of the iceberg of the number of cases that are actually reported compared to the number that happen. Of the people who felt ill after the Louis visit, how many of you actually went to a hospital or doctor to seek care? Case in point. Spike on the tip of the iceberg. Right. So the beauty of assessing things with a smartphone-based collection, I didn't show the eating, but when they were asked about eating, they could take a photo of what they were eating and could submit either with audio or text a description. And a surprising number did provide descriptions, some of which sounded pretty good. These provide some understanding of some of these missing pieces. I call it subclinical. It's not the right word for it, but illnesses that did not lead to clinical presentation. Cheryl is very interested in accuracy of recall, as was I. How well could they actually recall from an earlier time where they went, because that could factor a lot into how much automatic recording of where they've been could improve the accuracy to zero in on a contaminated vendor, how much they were actually seeking food at vendors, their risk perception, etc. So we could, in principle, inform risk perception. We actually didn't collect it. And this sort of data can inform parameter estimation, understanding, okay, how many cases might go, for example, for clinical presentation or not, how quickly they return back to a state of standard feeling well and, in fact, of seeking food and engaging in external food-seeking behavior. This is work which Aiden's been doing. Cheryl had a student, Patrick, who did a really nice set of basic analyses, including many related to recall ability, which showed differential recall ability for different foods, and does raise big questions about the degree to which collecting data on an outbreak based on someone's presentation and illness perhaps 2 weeks ago could really yield valuable evidence. It seems questionable if they can barely recall where they ate and what they ate last week. She has much more detailed understanding of the recall effects and how they vary by food type, but recall is certainly very limited. For this study, we actually examined to what degree, if we were to simulate a situation where we had individuals with a small sentinel group of individuals, say 4% of the population, carrying a system like this, reporting over time, allowing it to report where they went and reporting where they ate and reporting illness, even if it didn't bring them in for clinical presentation. If they could report that, and if inspectors could know about these reports and act on them, how would it affect the ability to lower the burden of foodborne illness within the population by shutting down contaminated restaurants? And while a very early study, and one beset by some substantial uncertainties, and one that has to be really redone in light of the later evidence, we did find a big impact. The estimate was 60% in reduction of illness, not of severity to bring them into doctors, but such as some of you faced based on your adverse eating experience the other day. With just 4% of the population of sentinels, this extra information from so many more people about where they felt ill and where they went as measured by the smartphone could allow for cluing into where might be contaminated restaurants. It doesn't have to be perfect, it doesn't have to be a silver bullet, but if it could motivate more judicious inspection of restaurants on the part of an inspector so that their time is better spent, it would lead to potentially large gain. So one of the biggest gains here, when we think about this in relation to dynamic modeling, lies in using data from these sort of systems to evaluate which interventions have been changed by an intervention successfully and which have not. The hope here, by examining the impact of an intervention, not just on broad outcomes like obesity levels, but the particular pathways by which those have been achieved. For example, following a move to a mixed income neighborhood on the part of a poorer family, the degree to which that has changed their use of recreational space or walking in the environment due to the walkability, lower sedentary behavior, for example, and increased moderate to vigorous physical activity. The degree to which it's led them, for example, to engage in shopping for healthier produce and fresh foods, changing their healthiness of diet. The degree to instead, to which the obesity levels, say, in an adolescent, have been instead mediated by the number of meals they take at home. We can start to delineate these different pathways which contribute to these different effects. This particular example was drawn from the Moving to Opportunity study in the States, where we did see improvements in obesity levels for teenage girls following a move to a mixed income neighborhood, but it wasn't clear what the pathways were. Improved physical activity, lowered sedentary behavior, better access to better foods, higher access to recreational space, easier walkability, higher levels of perceived safety, and therefore greater use of moderate to vigorous physical activity. If you can't measure things in terms of location, where they're spending their time, their dietary intake, reliable indicators of physical activity, and who they're spending time with, probing some of these pathways here or in other contexts can be challenging. But once you can measure those things, you can quantify the time they spend at home, the degree to which they're going to grocery stores and what they're purchasing or eating from photos of their food or from photos of their receipts. We can look at their moderate to vigorous physical activity. We start to come to understand the particular pathways change from their earlier time in the lower income neighborhood to their new neighborhood. And that can start to give you a picture as to why you see these effects, why you see this change in obesity level. Or, in the same study, perversely why boys' levels of of obesity did not improve by a statistically significant level. What was it that was different in boys? One of the hypotheses was they were going and spending more time in the old hood. That accorded with observations that their pro-criminal involvement was higher following the move to a mixed-income neighborhood. But without ways of measuring these things more reliably, it's hard to be sure because self-reporting can be misleading, can be confabulatory, etc. With the right ways of measuring these things, we can better understand these pathways. Now, not 4 days thence, in this very classroom, I argued that much of our job with simulation models is to reason about these pathways. It's to have simulation models that capture these different pathways. And this is one of the big ways these models come together with this high-resolution data. High-resolution, high-velocity data on a pathway-specific basis can be compared to high-resolution, pathway-specific data that's high-velocity from a simulation model. A simulation model can be better checked, better learned from and improved, challenged and improved using data from these sort of fine-grained data collection. It can also be better parameterized and calibrated using this data, but also better tested in its predictions, including predictions of intervention outcomes. So in short, that picture that I gave on that opening day of models as learning tools can be accelerated yet further through collection of this sort of data because it provides us this specificity of pathway resolution at a high velocity level that is comparable to what we get out of a simulation model with high velocity, highly specific data. And it provides us critically from a public health perspective with the opportunity of learning from interventions more deeply. When an intervention falls flat, not just saying, well, it's not efficacious, per Jeff's comments as the critique of traditional intervention evaluation, that this is not an efficacious intervention. It goes to why wasn't it efficacious? More of the questions and under what context would it be efficacious? The questions that are elevated by critical realism in the work of Pawson and Tilley. So in this case, ladies and gentlemen, if we fall flat in our goals for improving obesity within teenage boys, we can start to ask why. Where do we succeed and where do we fall flat? With teenage girls, why didn't we see more of a gain? Is it because we improved moderate and vigorous physical activity but not lowered their sedentary behavior? You know, are we achieving lows and obesity because they're spending more time eating home-cooked food, but we're not able to achieve that change in walkability? That can lead to better interventions. The ability to learn more quickly, more deeply, more reliably from interventions as well, with and without models. With and without dynamic models. Dynamic models providing an extra level of ability to ask about counterfactual interventions. Many other studies we've run with this system. Ethica has now been used, it and its predecessors, between 75 and 100 studies worldwide, some in the fair continent of Australia. It's reached even yet the fatal shores. as well as Europe, a number of countries in Europe and across North America. Some other fascinating work in tobacco use and e-cigarettes, highlighting the incredible differences between cigarette use on the one hand and e-cigarette use on the other in terms of how the devices are used, with cigarettes being used more episodically and in discrete intervals. The cigarette burns down, I'm done with my smoko, and I'll go back inside. Isn't that right, Jeff? Well spoken. By contrast, with e-cigarettes giving us a picture of these long intervals of more or less continuous hits from the e-cigarette during much of the day. No real discrete smoke of an e-cigarette. I'm going to go out and take an e-cigarette because it goes on for hours and hours on its cartridge. It can last perhaps 8 hours of more or less continuous vaping. Pick it up, vape, put it down, and you can imagine the impact of that on nicotine addiction levels. So in short, sensors and dynamic models. How do they work together? Sensor data, data from smartphones, not just sensor data, it's microdata collected from wearables, collected from smartphones, collected by microsurveys. It helps us ground the models, ground them in high velocity observations. It helps us reground them using techniques Li Xiaoyan is about to speak about. And it provides databases for parameterization and calibration on things such as location, contact patterns, physical activity, sedentary behavior, dietary intake, knowledge, attitudes, beliefs that are traditionally hard to gather reliably at a micro level. Dynamic models can help us make sense of this cacophony of data, capturing the underlying regularities that help explain it, helping us reason about counterfactual interventions that are different from what we've seen, but can benefit from that knowledge of what we've seen through incorporation in a model that we can then ask what-if questions. It can help us understand the implications over time of what data we have collected from these mobile devices, for example, and fill the gaps between them. It can help us identify sampling rates that are suitable for our needs and motivate certain types of data collection. So I think I'll leave it there. I will just mention one very challenging, provocative thing. We've run a number of studies where we've collected a large amount of data, say on contact patterns, or on mobility patterns, and we've asked, suppose we were to not have collected that much data. Suppose we were to have collected data not every 5 minutes on people's contact patterns, but instead every 15 minutes, or every half hour, every hour, how about every 2 hours? How about 4 times a day? How about once a day? How about once every week? How about just once for the entire 3-month study? If we were only capture aggregate snapshots that are averaged over the entire time, or if we were to capture just a snapshot at a moment in time or at a short interval in time of contacts and use that as representative, how much would that change our impressions compared to capturing this constantly changing dynamic network measured every 5 minutes? And so we perform these data knockout experiments. We say we have all this data, let's knock out large portions of it, pretend we only measure less frequently, for example, and see what the difference is. Windchill, ladies and gentlemen, is a master at these things. We did so with simulation models and said, okay, if we had run the simulation model with the full set of detailed data, measured every 3 minutes or every 5 minutes, and we compare that with the conclusions we get out of that with the conclusions if we only measured it every 3 hours or once a day, how would it differ? And the answer is it differs in pretty big ways by factors of several times. Working with a typical day is just not adequate. We get, with a fully detailed simulation, a quite different picture than we get with a fully sort of an averaged graph. Importantly, our expectations of the burden of infection in terms of the prevalent cases, for example, over time, is very different if we sample every 3 hours than every 5 minutes, because we capture a lot of contacts that wouldn't otherwise be captured. And more recently, this is actually an old graph, but more recently we've performed this sort of analysis over a wide variety of conditions, about 10 different infectious diseases, things as varied as norovirus and H1N1 influenza and fifth and measles and pertussis, etc. And we've seen that some of those infections are very sensitive to how quickly we collect data. Norovirus is a good example, or measles. They require more frequent collection. Something like TB is a classic example of something that doesn't require frequent contact because the latent periods are so long that it spreads very slowly, and the details of your contact patterns are unlikely to add much value. Winchell is the master of this, and I'd be glad to refer you to him if you're interested in getting some of the latest updates. So, closing remarks. I've shown you a heck of a lot of stuff. Ladies and gentlemen, if I to summarize with a single phrase, I'd say the future is bright here. There's a natural marriage here between system science and data science. Electronically captured data, big data characterized by high volume, yes, but more importantly by high velocity, by high veracity, and high variety, is increasingly ubiquitous, and it shares many of these features, certainly variety and velocity with dynamic models. And it shares the ability to resolve certain pathways with those models. Commodity sensor-bearing devices, smartphones, wearables, for example, can serve dual use as sensor platforms, EMA issuing platforms, and crowdsourcing platforms. They're incredibly flexible, and increasingly they're drawn together. We use Ethica now with wearables. We've used it some with a couple types of wearables, not just Fitbit, with some which seek together as well heart rate variability and electrodermal activity, for example. And at the same time, empirically grounded models benefit from data, and in some cases require data. Coupled with models, this sort of big data can offer really significant and complementary health insights. We can use the models to tell us how frequently we need to collect things and what we can best collect to prioritize the data collection. And the data can inform these models in big ways and can reground them over time in a way that will be suggested by the work of Li Xiaoyan, shown shortly. Although she's worked with more traditional data sources, it shows this principle of regrounding. Cross-linked sensor-based and EMA data, as well as other components of big data, offer a huge amount of potential to complement and sharpen dynamic modeling. The sort of modeling that we're conducting here has a very bright future because the ability to inform it, to get it out of the realm of speculation in terms of microbehavior, and to transition it to a point where it can be grounded and our hypotheses can be challenged as captured in the models, and we can use them ever more effectively as learning vehicles. Use of additional machine learning techniques can really substantially enhance the power of dynamic modeling. I'm a big believer in combining dynamic modeling with machine learning and AI techniques. CCM falls broadly in this category, but so does particle filtering, particle MCMC. And a key use of data for social and health policy, in my view, is to learn more quickly from interventions. It's to learn more deeply about what is going wrong with an intervention so we can improve it. We can make it better next time. We know not just that it fell flat, but increasingly where and why it fell flat. And with simulation models, we can ask what if we were to change this or change that and come up with a better plan, a more informed plan, a more judicious plan. Ladies and gentlemen, I am grateful for your attention for this long lecture, and I would invite you to the food which has been waiting outside for far too long. Thank you very much.